Whereas if you have a branch structure like this, you've got hundreds or thousands of these non-reducing ends, each one of which can have an enzyme hydrolyzing. So you can get like a flood of glucose real quickly because of the branch structure.
I'm sorry, this is the non-reducing end or the reducing end?
It's the non-reducing
That
ends.
gives off the glucose.
Yeah, all of these, the reducing end of these molecules is way back here in the center. And because it's branched, it's got many non-reducing ends. And these are the points where it's not attached to anything. At the very end of those chains, there would be an OH here and no other glucose. That's where the hydrolysis enzyme comes in and attacks. So there's a physiological logic to this branch structure. It provides a possibility of multiple parallel processing to get to the glucose. And as we'll point out here shortly, there's actually two ways to process it. This one, we're kind of getting a little bit ahead of the game, but if this was inside a muscle cell or a liver cell, it wouldn't hydrolyze it. Notice here we're adding phosphate. It does phosphorylasis instead of hydrolysis. It adds phosphate across here to give you a sugar phosphate. This is a high energy molecule, it's a lower energy molecule. By adding phosphate, we kind of save ourselves an ATP. Because if you are a muscle cell and you need that glucose for glycolysis, the first thing you're going to do is spend an ATP to phosphorylate it. This gives you a cheap way of getting to that stage without spending ATP to kind of exploit the fact that your polymer is a high energy thing. So you can break it down inside the cell by phosphorylasis.
And amylopectin and glycogen are both the ones that have